Hello everybody, I hope you all are fine. In this episode, which is the first session of season 12, we're going to talk about modeling with the plugin of Kangaroo. And also in this episode, we're going to talk about agent modeling, agent-based modeling, and particle systems within the Kangaroo plugin too, and also Kangaroo Physics. Actually, within the older versions of Kangaroo plugin. For the beginning, I start or open the Kangaroo tab to show the menu and the topics. The base of the physical modeling by using Kangaroo plugin. In fact, I'm talking about the older versions that we used to specify the strengths, the forces, and we also specify the Kangaroo physics or engine force and the object that we wanted to import the force. So we had the engine force, the forces, and the object that we wanted to force the import the forces. Here in the new version, which is simpler than before, the engine has changed to bouncy solver, and the forces are displayed as targets or goals. That here we got different kinds of goals that I want to make some examples in this episode. In this session, you're gonna learn how to use Kangaroo tools based on the practices and the examples that we make or we mention them. So then we can put them into practice and use them in your own projects. Here at the beginning of the practice, I'm gonna add 2 points into the canvas. After setting the point, here at the top view, I want to add points, set these points, and then I want to draw a line out of these points. Add another point, set 1 point, like this. Then we're gonna draw the line based on these 2 points, and then we're gonna determine the length of the line by using Kangaroo plugin, which is length. So we search for length, which is developed for a Kangaroo plugin. We give the line, then when we want to convert the length to 3, for example, units. Following that, by using bouncy solver, we should give the spring to the goal objects by this way. Then we can hide the preview of these and show you the results. Check it out, 3 units. In Kangaroo Physics, we called it spring, a spring from line, that it got different kinds of inputs, connection, stiffness, damping, rest length, upper cutoff, lower cutoff, and plasticity. That it has been simplified in the new version, that we got line, length, and strength. Anyway, here if I give the spring to the panel to show you the output, check it out, we got a Kangaroo solver goal spring. So we give the strings to the goal objects and then boolean toggle to specify on. Following that, the button for resetting, check it out, which is paused. As we reset it, we can reset it to the default mode, and as we turn it on or off, we can repeat the process. So let us talk about bouncy solver. I add bifocals to show you the name of the components and give you some other informations about these. The first one is iteration, that is the number of the repetition that it repeats the process, just like loop. It repeats the process until it converts the input to the output. I mean, it repeats the process until it converges, and the amount of movement of these 2 points is 10 powered in minus 15, I mean at least, and it takes some time to converge the process. And for the iteration, we specify the number of the repetitions. Here, as you can see, 20 for iterations. And for iteration, we can increase the speed or decrease it. For instance, 1. Check it out. It decreases the movement that we can observe when it is moving. Let us talk about the another output, which is v as least, which creates the particles or the points. Here, as you can see, we got the coordinations of the points which are associated for the primary points. And for O or O as least, let me give it to the panel. As you can see, the output is line. Sometimes we got meshes and so on. It is based on the given input. So, in order to make the process more complicated, I internalize these. Since we don't need to save the Rhino file, and I set the toggle to false. Since as soon as we open the file, the process of converging will be started to converge again, so the software may crash. So guys, this time I'm gonna add 3 points like this way. Check it out. Set multiple points, click and drag to set them in Grasshopper. Following that, by using polyline, we give the vertices to draw the polyline, and then we invert it to close the points, the curves actually. Then by using explode, we give the curves. Then I want to constrain the length of the segments to 2 or 3 units. I want to assign the lengths. I ungroup these and turn them off. Again, we search for length line. We give the segments. Following that, for the length, we specify 3 units. And then by using bouncy solver, watch this. We give the goal object, check it out, as you can see, the points are moved and the triangle is created. We add the Boolean toggle and also the button, just like the last one, for resetting the bouncy solver. As you can see, the curves are created. And again, I internalize these as usual, and I add the panel to give the iteration to panel 1300 times to converge the length of the line actually. Converge it. Here I minimize the speed. Watch this. 1. Check it out. We can observe the movement, or I increase the speed, check it out, like this way. So by this order, we can consider assign a condition for a line. What about the next goal is to keep one of these particles fixed. Then I want to modify the length of the segments. In fact, we can simulate these to some people or human, that I want the distance between them to be always at least 3 meters. So right now, if I want to consider one of these points as a fixed point, I want to use anchor. We add it into the canvas, and then for P input, we should specify the fixed point, in fact. In fact, we're going to specify a point which does not receive any forces. List item, and the next I need item 1, so we give the point to anchor. I hold down shift to give it to the goal object of bouncy solver. Then I click on button, check it out. One of them is fixed and others are moving. Then the other things that you'll learn them later, you can specify a target. We can assign these to another point. I move this point, for example, along z-axis at 1 meter or 1 unit. Check it out, and changing the target by this way. Firstly, let me turn them off and hide the preview of these as well. I show them. Check it out, this is the primary mode. Then I have considered multiple conditions. The first one was that the length of each of the segments should be converted to 3 units. And the second one, I have considered this point fixed. Following that, I wanted to move the fixed point at 1 unit along z-axis. Let us check it out. This is the converged position, and 1520 times to converge the curve. Let us move on to hide the preview of these, and then we're gonna talk about the next topic. In the next one, we're gonna make a catenary or a chain-like object, and the imported force for these objects are the weight of the objects. So firstly we search for a line, then we add it to the canvas, and also by using 2 points that I want to set them there. Check this out. Here in the top view, right click, set 1 point. I add 2 points and then I set them. Then I wanna draw the line between these 2 points. Following that, by using divide curve, I want to divide the curve into some polylines. Check it out. If I bake the line now, we will have a straight line. It is not splitted actually. So again, we use polyline, we give the vertices. Right now we have drawn a line, then we have divided it, and then created the polyline. After converting them to polyline, we can search for explode, then giving the curve to get access to the segments and vertices that we got each of them separately and independent to the others. We delete them. Let us continue. Then, in order to make the catenary, we should put some forces on each of these. So, here there is a point that you should consider it in Kangaroo plugin. We got only 2 parts for importing forces or applying forces, which are the points. If we had a curve like this, which is divided with points, the positions that we can apply the forces are the points. So the points are the positions that we can apply or receive the force. And the curves between the points other forces can be applied with other forces, like a spring. If we stretch the spring, it wants to return to the default mode, and if we put pressure on it, it wants to free itself. And we got the same behavior in the surfaces and meshes as well. We can apply the forces on the vertices, and we're not able to put the forces on the meshes or surfaces. Let us move on. We add the bouncy solver, and then the goal objects load. Here we need to load forces on the vertices. Check it out. Firstly, I give the vertices to point of load to apply the forces or load them, and then we give the result to goal object. Here in the perspective view, I add the Boolean toggle. Watch this, and also the button for resetting the bouncy solver. In the next stage, for FV, we should specify a vector and also a value or a number, which is the force. For instance, along z-axis and 1.5 for the factor. Following that, for the segments, we add length line. We give the segments to give them to the goal object. And as you can see, the speed of the movement is too high that I should zoom out to show you the movement. Check it out. It is moving along z-axis. Great. And in order to show this in a 2D view, succeeded fault, and this time I want to use unit Y instead of Z to show you the movement in the 2D view. And in order to constrain the movement, I want to keep the first and the last points fixed. We add the anchor to constrain the first and last points and keep them fixed. We give them points, and then to the goal object. Watch this. This is the result. We can increase the factor or the loaded force, as you can see, and even we can flip the direction. We can define minus x, then it moves downwards, as you can see, or we can disconnect it from one of the sides or ends. Here, let me consider it. Firstly, we have added 2 points, which are the 2 points, the 2 primary points, or the 2 input, and then we have drawn the line. Following that, we have divided it, then polyline. Check it out. We have exploded the polyline. Watch this, to get access to the vertices and segments, and then by using anchor and length and others, let me align these. The first thing was constraining, selecting the first and last points, pieces, and constrain them or make them fixed, keep them fixed. After considering these 2 points, the first and the last as the base, these 2 points are disregarded in applying the load. Then we have regarded the forces, or we have loaded the force for the other vertices and segments. Check it out, and then we made the model object. Here in O, check it out, O output, we got the lines. As you can see, within the lines we got some null items inside the list, as you can see. And in order to remove the null items, we can use clean tree. Check it out. And then if we give the list, it removes the null items. Following that, by using line dimension, we can display the length of each of the segments or lines. I minimize the size. Then, as you can see, the sizes are displayed. We hide the preview of others, and we can check out the length of the lines. The segments which are close to the base got longer lengths, as you can see, but the segments in the middle got less lengths. If I remove one of the bases or backrests, check out the first segment, 1.8. The bouncy solver is running the process, check it out, 3,350 times to converge these lines. First one 1.8, second one 1.71, 1.62 to 0.99, nearly 1. And the reason of these dissimilarities between the lengths is the imported loads. I mean, we can simulate these to some climbers, for example the first one, which is pulling the second one, and the second one is pulling the third one, and so on. So the first one should have the greatest force and strength, and also higher tolerance level. So this was the dissimilarity of the lengths, and we talked about these as well, and we managed to create this just like a chain. However, we can work on it more. For instance, we disconnect these, I set this false and hide the preview of these, and also turning on this. Then in the continuation, I want to add one more point which is placed at the middle for the base point, or to keep it fixed here by using list item. Firstly, we give the divided points to the list, then in the panel we should specify the item, the first one, and then the last one, let me check it out, which is item 11 and item 5, multi-line data. Then I give it to items and then to point. Watch this, this is the result. Actually 10. Watch this. So this is the result. We got the connections from item 1 to 10 and from 10 to 15. I mean 5 to 10, I'm sorry. So this is the chain-like object. Check this out, 0, 10 and 4. And if we wanted to move them along z-axis upward, we can remove the expression. Watch this. This is the result. Then we can specify the moving factor. So guys, this was the general concept of the processes in Kangaroo by using these points. I ungroup these, set it to false, and I wanna move on. I hide the geometries, then I draw a rectangle like this, curve, to set the curve, then I internalize it, I delete the object in Rhino, following that by using populate 2D to create the points inside the rectangle. Let me minimize the number of points, for example 7, and then by using the learn tools like Delaunay edge or edges to draw some triangles inside the rectangle. Then I give the edges to explode them to the segments and vertices, and I need to extract the center point. Check it out. I mean, I want to keep the centroid fixed but others movable. To do this, I'm gonna use list item to extract the selected item at first from the list of points. We give the points, and in order to recognize the index number, the centroid, let me check it out with point list. Since I need the centroid and I need to know the index number of this, firstly I show the numbers by point list bake, which is number 4. Great. And then I define 4 in the panel, I give it to index, and then I want to give it to the point anchor like this way, And then I should search for length line like this, and 3 for the length, a specified length. In this part I flatten the exploded segments or to remove the groups or branches. Then bouncy solver, the goal objects, watch this, and this is the final result, like this way. And I consider the button for resetting the bouncy solver. Watch this. This is the converged result, as you can see. Then I can modify the length like 4. Then we reset it to apply the new changes, or 5, again reset. Check it out. We got the regular geometry. Then let me modify the number of the points, for example 6. Check this out. Increasing them, then resetting. This is the created geometry, which is different to the previous one. 3 for the length by this way. All in all, we can draw such a geometries. There is no limitation. We can even work with open curves, not necessarily the closed curves. And then we can apply the changes or considering the conditions to consider one or multiple points for the base points and a unit length, and then applying the specified length on all of the segments. We consider a value for seed. Watch this. This time we got a different geometry in compared to the previous one. All in all, it depends on different items or cases, like the length of the points and seed, and also the length, the number of the points on each of the segments, and also specifying the points as the anchor. For example, item 3. Watch this. We can draw different kinds of geometries. Maybe in the future sessions I exemplify other cases. I set it false and I ungroup these, hide the geometries by this way. All in all, we got familiar with the main concepts of Kangaroo plugin, and in the next episode we're gonna talk about loading forces on meshes and also the surfaces. Right now we're gonna load the forces to the meshes instead of to the lines and curves, because in the last session we worked with the lines and the points. So the first thing that I wanna do here is to add a mesh plane here, mesh plane, to draw it like this in the perspective view. Here, as you can see, in mesh planes we got the similar behavior just like lines. They behave just like the springs. We got some vertices and the lines between them that we want to import or load the forces to the vertices, just like the springs. So guys, we got the same thing in the meshes. We got the vertices that we want to load the forces upon them, and the middle edges provides us the pushing and tensile forces. So, and in order to begin the process, we need the edges and the vertices. So I want to search for mesh edges. Check it out. To extract the edges or mesh edges of the surface, here we got 3 types of edges: E1, E2 and 3 naked edges. For example, the first one gives us the naked edges, or the edges which are placed in a single mesh or on a base. Let me show you in a curve. Watch this. These are the naked edges, as you can see that we got them, which got exposure with the outside environment. And E2 connects the segments of the meshes to each other. As you can see, these are the edges. And E3, that we got no edges of this type. But in order to show you this type of mesh edges, I wanna draw another surface, and then I want to show the mesh edges of E3. Check it out. And then vertical. Watch this. Here we got three surfaces. Here the edge which is placed or positioned at the middle or at the intersections of the three surfaces is E3. So guys, we have obtained the mesh edges. Then in the continuation, by using length component to apply the spring-like forces. And then we need to extract the vertices as well. So I want to use the construct mesh. We use the search for the first words DECME, and then I add the construct mesh into the canvas to obtain the vertices, faces, centers, and others. We give the vertices to load since we want to load the forces on them. Then in the last part, I want to consider the four corners or the four vertices at the corners as the anchors. Bouncy solver. We give the length and the vertices. Watch this. As you can see, it is moving upwards. Here I add the toggle to turn it off, and also the button to reset it to its default mode. Then we get back to the process to show you something here, and then I give the goal object. I do not specify a load for now, and then I want to talk about the vertices at the corners. Here we add point least. I give the vertices to show the point least. I bake them. Watch 0, 10, 110, 120. So we can define these inside the panel 0, 10, 110, 120. Right click multi-line data, and then by using list item, we can give the list and extract them from the list of vertices. And then I want to give them to the point of anchor and then goal objects. Right now we have specified the fixed items that are going to be fixed. Check it out. This is the result, just like a net. Here if I disconnect the load and also removing the anchor, then this would be the result. I hide the other parts to show you, and then I give the load. Check it out, they are moving upwards since we haven't specified the anchor. But if I give the anchor, check it out, after specifying the anchor, it moves until it reaches to the balanced position. And as you can see, it is still running and it is not converged. Well done. And in this model geometry, we needed nearly 7,000 times for making the object converged. And the other things that I wanna do, I wanna show the meshes since here we got only some curves and vertices. So to do this, we're gonna use show. We give the mesh and then we give it to the goal object for the bouncy solver. Check it out. We can show the mesh like this way, and then for the output, let me hide the geometries of these. The first thing to do is using clean tree to delete the null items, and then by using list item, we want to extract the item. As you can see, we got the lines and the meshes in the list. So by using list item, we give the trimmed list to extract item tree or the mesh, and then we can work on the mesh independently. For instance, we can use subdivision in Mesh Plus plugin like snub plus 0 and then giving the geometry and creating such a panel on the mesh or surface, and then cat null subdivision to subdivide or smooth the mesh at 3 levels. Check it out, this is the result. Then let us check out the object from the beginning, again button to reset it. Watch this. And as you can see, it takes some time since at each of the stages or at each of the frames the mesh is being subdivided, which takes some time. Suppose that if I wanted to pause the process of converging, for instance, I need to pause this. Suppose that I need this geometry, I don't want it to be converged, so I pause it, I set toggle to false, and then we will have it converged at this way. Then I bake it to check it out in the rendered viewport. Well done. We delete these, disconnect them to reduce the volume of the file. Up to this point, we learned about the things that we can do with the meshes. We extracted the mesh edges, and then we have extracted the vertices and also the corners. I make a copy from these and then I paste it here. I set this to false and I can turn the previews off and then group them. Then for the new example, we can modify the dimensions of the mesh planes. We can specify 20 in 20. Watch this. The first thing that we observed was such a geometry since the anchors are changed because of changing the dimensions. I have reset it and this is the result. In fact, we haven't specified or selected a correct or a proper method for specifying the anchors. I set this false, and then I want to have the corners. Again, we can use join curve to convert the edges to a square, and then discontinuity, we give the curves to discontinuity, and then I want to consider the vertices as the anchors. Check it out. Right now we just obtained the vertices faster than the previous one, and if I even modify the dimensions, still the anchors are fixed. Here there is no problem or a change with the geometry. 15 and 15. In the continuation, I'm gonna specify other points to set them as the anchors. Again, I want to obtain the list of the construct mesh. We give the vertices, and then here I can make a copy from anchor to give the items to the new anchor, and for the I set this false since I'm going to specify new vertices for the anchor. I set the number slider so we can check the selected item in the list. Check it out. For instance, item number 7, this vertex. I want to consider it as the anchor. Watch this. This is the result. Then after having it converged, here we can right click on list item, internalize the data, set it false, and then by using the tools here or by using Weaverbirds tool like frame or mesh window, check it out, we give the meshes, hide in the preview, And then having such a panels, then we can assigning different materials to each, for example to windows or frames, or for mesh and window we can combine it with mesh plus plugin. Let me choose one of these tools like this, frame plus 2, and then specifying the distance. Check it out. As you can see, they are extruded. Let me specify the domain a negative value to move them toward inside. And this is the result. Bake. Then we can check it out in rendered viewport in the perspective view. Watch this. So guys, we managed to create such a thing out of the meshes, and also we could have used subdivision, Catmull Clark, to subdivide the mesh or smooth it, and after having it subdivided, then we can bake it and check it out in Rhino. I disable these. We don't want to watch, we don't need to preview. We ungroup these. Let me make a copy from these. Then we're gonna move the process forward. I remove the anchor, the middle anchor, and check it out. I show the preview. The next thing to do is to simplify this part. Here we have used mesh edges, and then we have given it to length. For applying the forces in Kangaroo 2, we are provided with another tool. Here we can type edge and then add edge lengths, and using this tool instead of mesh edges and length line. So it simplifies the process. Since it has done the process, it plays the rule of two components. Then let me give the output by holding down Ctrl and Shift to check it out. So we delete others and then replace edge lengths of Kangaroo 2 or Kangaroo 2. And then we should consider the anchors as well. So as we deleted the mesh edges, so the corners are deleted. But we can replace it with replace mesh corners to find the corners of the boundary of a mesh. Watch this. We give the mesh and then it gives us the corners of the mesh. Instead of specifying the items in list item and extracting them, this method is easier than the previous one. And at the last stage, we'll talk about the height. I'm gonna do something for the load. I set it false. I reset it here instead of using load manually here in Kangaroo or Kangaroo 2, which is vertex load. Check it out. To apply equal vertical loads to all vertices of a mesh. We give the mesh, and then the forces will be applied, and then we can have it like this. And if I want it to be moved toward up, we can specify Z unit or unit Z and specifying the height like 0.25. And as I minimize the value like 0, we can move it or specifying the position of the mesh. I align these components, and as I showed you, this was simpler than before. And if I want to add some more vertices for the anchors, we add list item. For instance, 125 like this. Let me move it in the top view. For example, here we can select this item 134 to consider it as the anchor. Check it out. This is the result. And then we can bake it and directly using the surface or by using Cadmo Clark. Again, list item 0 to subdivide it, which is the mesh, and then we can bake it, or we can use other tools that we can find them in Weaverbirds plugin or Mesh Plus to make some other modifications upon the mesh or surface. Following that, we can bake it and check it out in Rhino. I set it to false, making a copy, and I ungroup these. The last topic that I want to talk about is a tool which is Grab, which lets us to drag Kangaroo particles in Rhino viewports. We give it to goal objects. It is very interesting. And then in Kangaroo, Grab, you can find it. Right now I'm gonna disconnect all of the loads of bouncy solver, and I also disconnect the anchor as well. The loads and the anchors behind the previous geometries, and then let us check the new example and also deleting these. I want to hide the preview of the previous ones. As I told you before, in Grab, now lets us to just click and drag the mesh. We can click on the mesh and then grab it to load the force or apply the load. Watch this. We can totally control it manually by click and drag. Here if I use Cadmo Clark to subdivide the mesh, check this out, and display the mesh in a smooth version. Then in Mesh Plus, Weave, we give the geometry and specifying the parameters, vertex width, edge width and face width. Then I increase the edge width. Watch this. Like this way. Again, we want to subdivide the geometry after weaving it, like this. Check out the results, 3 levels for the subdivision. We created this geometry so simply, and even we can thicken the mesh by Weaverbirds mesh thicken, not 0.2 for the distance. Then we can subdivide it, bake, to check out the baked version in Rhino, and then by using graph to modify it. Let us check it out. It takes some time and the process is too slow because I have not set this to false. But if I set it to false, then it will be accelerated. Check it out, guys, in the rendered viewport, which is great. A model that enables us to modify it even by clicking and just by clicking and dragging without any difficulties. We hide it and I show this part. In order to reduce the volume, we can disconnect it and showing this. So again, by using the grab here, I want to click and drag and modify the mesh. And since we haven't considered any loads, we can easily modify the mesh. And then we can consider the 4 corners by using corner and anchor. Watch this. To consider the constraints and then move them. And whenever you wanted to save the changes, you can set the toggle to false. Then let me thicken it and bake. Well done. Check it out in the rendered viewport. The process is finished. However, we got too many tools in Kangaroo, no plugin. I mean, you can use others like Weave, Volume, Subdivide, Smooth, Weaverbirds, and so on. They could all be practical. Let us begin the next example. Here, at the beginning, I'm gonna add the plane surface to draw the main surface, and then we'll specify x and y dimensions for the width and length of the rectangle. Check it out. After drawing such a surface, I'm gonna use the panels in Launchbox to let us search for them, like triangle panel C. Then I give the surface, then I divide the surface into these panels. In the continuation, I want to convert each of these triangles to some meshes. So we search for simple mesh, we give the panels to be rep, and then it converts them to the meshes. And as you know, surfaces with 3 or 4 segments are supported by simple mesh to convert them to meshes, and then we can use them. After doing this, after using simple mesh, I'm gonna search for join mesh to join all of these meshes. Check it out, nearly 400 meshes. Then we will have a single mesh, and these meshes got some vertices that are overlapping, so mesh weld vertices, and then we delete the duplicated vertices. We hide the preview, and this is the final mesh. In the continuation, I want to extract the 4 corners to consider them as the 4 anchors. So curve at first to extract the edges, following that discontinuity. Then I give the curve, then we will have the 4 corners. Then in Kangaroo, bouncy solver, then by using anchor, we give the points, and after considering them as the base points, we give them to goal objects. Then edge lengths, that we learned in the last session, we give the mesh, and then the output to the goal objects, like this way. Then we will have the connections between the vertices, which is the spring-like connection. Then by using vertex load, I give the mesh and I apply the loads. Check it out. This is the result. But here I'm gonna teach you something else. The first thing, here as you can see in anchor, we got the point for input, and on the T, which is the target, and also the strength, as you can see. For instance, we can specify P or points by a point parameter, and then I internalize the point, and then I give them to the target. Then let us move the anchors. Watch this. By this way we can modify the geometry or the mesh, and if we wanted to show the mesh itself, we can use show. We give the mesh for geometry, and then giving the geometry to goal objects of bouncy solver. I select these instead of point, except point, then I hide their previews. Let me set this unordered, and then by clean tree I want to delete the null items, and list item to extract the mesh, only the mesh. However, we could have used the button for resetting the converging process and also the Boolean toggle, and then setting it to true for turning it on and off, and then we can change the target or the anchors. Check it out. Here we can give the points. As you can see, the targets have been returned to the default mode. Again, internalize and moving the targets like this way. Check it out. So we can do such a things, and finally, after creating the mesh, we can use the tools that they make the mesh relaxed, like the Catmull Clark to subdividing to smoothing the mesh, level 2 for the level of the subdivision, and then baking the geometry. Let us check it out in the rendered viewport in Rhino. Watch this. Here is the result. I delete it, and then we're gonna move on in Grasshopper. Up to this point, we learned that we can use anchor and specifying a new target for the anchors. Here, I give the points of discontinuity to point. Then in this part, I want to consider some of the points on the mesh as the anchor. I turn it off. For example, I'm gonna select one of these. Here we can bake the mesh, and then I should place or put a point on the vertices. Here, as you can see, don't forget that the point that you want to consider it for the anchor should be totally placed on the vertex. I mean, we cannot place the point on the panels because it should be exactly put on the vertex actually. Then I set the point that I just have placed on the vertex. Check it out, and then I want to give it to anchor or making a copy from anchor, and then giving the result of anchor to goal objects. Then check it out, I have turned it on. Here is the new anchor we just specified, and also we can move it, and as soon as we move the point, it will be disconnected from the mesh by this way. But now the question is, how do we can change the position of the new point that we just have put on the vertex? Since right now, as we wanted to move it, it's disconnected. I mean, we don't have enough time to bake the mesh and then add a point on the vertex and again adding the anchor. No, it takes some time, so we need to use an alternative way. The first thing to do is to use evaluate surface. Then we give the surface, as I told you before, we're gonna create some points on the surface. I add MD slider, and then I should parameterize the surface. Then I can use MD slider to create a point on the surface. As I told you before, we cannot consider this as an anchor, since as you can see it is not placed on the vertex. But I want it to be placed exactly on the vertex. What should I do? Here we got a tool which is closest point. We search for it and add it into the canvas. We give the point following that by using the construct mesh to deconstruct the mesh, and then considering the vertices for the cloud. Here, as you can see, we got the closest point on the vertices, which is given to us by the closest point. So then, by using another anchor, we disconnect this, and then giving it to goal objects. Watch this, check it out. And here, if I move the MD slider, we can change the place of the anchor, as you can see. And if I wanted to move them upwards, here in vertex load, I specify unit Z for the strength and also the factor, not 0.25. I minimize it, check it out, very well, hide the preview. So by this way you can modify the place of the anchor. According to the previous lessons, we can use the meshes here. Here I open Mesh Plus, and then I'm gonna use the tools from subdivision, volume, or weave. For instance, in sub-D or in subdivision, like this snap +1, then we give the geometry, check it out, and after making these, we want to subdivide them or smoothing them by Catmull-Clark. Check it out, and this is the output. Great. However, we could have thickened the mesh and also specifying the distance. Check it out. To extrude the mesh like this way, and then let us check it out in the rendered viewport in Rhino. Then let us talk about the next topic that I wanted to mention it. We disconnect here, and I show the preview of here. Right now I want to consider multiple points for the anchor instead of only one. So to do this, I make a copy from these all. I select them all, and then I ungroup them and turn it off. So in this part, in the new ones, I'm gonna use another thing, closest points instead of closest point, since we're gonna consider multiple points as the anchor, not only one. As we use closest point, we've found closest point in the point collection, or the closest point to the specified point in the mesh. But in closest points, we can have multiple points which are close to the specified point. Let me reset the top part, and I turn off the preview. So in relation to the point, check it out that we got it by MD slider. We give the point to closest point, and then in cloud we should give the vertices actually, and then for error number we should specify the numbers that we want them close to the MD slider, for example 5. Then as I move the MD slider, we are selecting 5 points, or we are snapping them. In fact, we are making snaps for the vertices, and as we move the MD slider or the control point, we are snapping on the other 5 points. We give the points, and then As you can see, we can consider them as the anchors. So right now you know how to consider more than one points for the anchor. However, we can control the number of the points and making different kinds of geometries. And still we can move on by Catmull-Clark subdivision for smoothing the geometry, or the tools in Mesh Plus to creating the panels on the surface. And let me ungroup these parts. Session we're gonna continue talking about the tools in Kangaroo plugin. In fact, we're gonna talk about the tools in Go's collage, as you can see. So to do this, I will exemplify many cases, many famous examples that you may have encountered with them before, since these examples are very practical in teaching Kangaroo plugin. Firstly, I draw a deformable circle and then I select the control points and move them downwards like this way. I'm just trying to draw something like a bowl and then set one curve. I set the curve inside the grasshopper. After internalizing the curve, we can delete it from right now. Then in vector, we add populate 2D, set one rectangle and drawing a rectangle like this way for the bound that I want to place the points inside. Then in the continuation, I want to apply some forces on these points along the Z direction, and then I want the points to be collided with the bowl like a container. So in Kangaroo, I want to add load. Then let us specify the force vector along Z-axis, unit Z, and also we're going to use negative. Then we give the result to force vector, bouncy solver. Then here for reset, we should add button and boolean toggle for reset and on as usual. Very well, and then giving the load to goal objects. Here the speed is too high, so we need to reduce the speed of collision. Let me add a value here, not 0.002, and then I reset it. Check it out. They are falling, but the points are not collided with the curve or the container since we haven't specified the condition. So here in goes collision, in curve point collide, that it receives some points. Check it out. And also a curve. Here the curve is the object that the points are going to collide with, and I hold down shift to give the result to the goal object, and I reset it. Check it out. Still the points are not collided with the curve because the pre-specified plane here is xy, that here we need the plane of xz. So we search for xz plane and then we specify the plane, and then again we reset it. This time let's check it out. As you can see, as soon as they collide with the curve, check this out, all of the points are collecting and overlapping each other. Here we can consider a value for the radius for each of the points and consider them as some balls or spheres. So in the next part, let me minimize the number of the population like this way, like 30 or 35. Then in the continuation, I don't want the points to overlap each other. So, as I told you before, we should use spheres. Here right now we pick sphere collide, and then we can give the points and specifying the radius for the spheres. But before that, let me show you the result. Check it out. Here from V output, I can give them to the points of the circles like this. And also we can give the XZ plane, check it out, and hide the preview. As you can see, we got these spheres collided with the curve and overlapping each other. It's time to specify the radius for both radius and the sphere and the circle. So right now there would be at least 65 centimeters between the spheres. We give them to the goal objects and then we reset the process. Watch this. We have defined two conditions. Firstly, the distance between each of the points should be at least 65 centimeters, and I have constrained the points not to cross the curve. As we have specified the XY plane, XZ plane, and the circle, we have limited the movement of the points. Here, if I increase the radius, check it out, just like an explosion. Watch this. Some of them fold. Again, we minimize it and reset the process, so we can have the objects like this. But here the only problem with the objects is that the points, as you can see, are collided with the curve and the circles are crossing the curve. So if we want the circles not to cross the curve, we should offset the curve. And it may reduce the precision of the project, but we can ensure that the circles will be tangent to the curve. So to do this, I'm gonna use offset curve. We give the curve and then specifying the offset distance, which is the equal to the radius of the circles. And then we specify the XZ plane like this and then give it to the curve. Check it out, we can hide it and then we reset the process. Right now, as you can see, the curves are tangent to the curve, and this is what we exactly wanted to be displayed in the scene. Let us have a review. Firstly, I have drawn the curve. Here it is, as you can see, and populate to 2D to add the points inside the rectangle. Then I wanted them to be fell and be collided with the container or curve. And as you can see, I wanted to move the points along z-axis, and I have used negative to move them downwards. And then I have defined two conditions for them after adding the curves and points. The first one was we wanted the points to be collided with the container or the curve and do not cross it. And the second was the points should be at least, the minimum distance was at least 0.65 parameters. So we used curve point collide and sphere collide, and finally by giving v to xz and circles that the radius is equal to the distance to the radius of the spheres. And at the last part I have offset the curve to have the circles tangent to the curve. Let me show you the previous mode. I reset it. Check this out. The points are tangent to the curve and the circles are crossing the curve. That to solve this, I decided to offset the curve. Watch this. Then I considered the offset curve for the curve point collide. Watch this. So right now We got the circles tangent to the curve and they are not crossing the curve, and this is what we wanted to display. So guys, we're done with the first practice. We can group these and we can hide the preview and move on. Here in the perspective view, let me start the next practice. Firstly in Rhino, like Taurus, and then I draw like a tube like this. We got a tool in Rhino which is drape. By drape we can draw a surface. Check it out. That it simulates an object which is covered with a blanket, as you can see. In other words, it seems that we have put an object under the blanket. So this is the result of drape, that the surface is stretched. But right now I'm gonna simulate, a blanket. So to do this, firstly brep, and then I want to set the brep in Grasshopper, and then I internalize it so I can delete it from Rhino. All in all, here we got an object that we want to place the surface on it, and then by using a surface that I want to draw it in Rhino, a planar simple and plain surface, I hold down shift to have it a square shape. Then I want to move it to place it exactly at the origin point. Then I move it upwards, following that by using mesh surface to convert the surface to a mesh. However, I haven't set the surface yet. Check it out. And then we give it to mesh surface. I internalize them, and then we can delete them from Rhino. Then let me increase U and V counts like 20 for both. Hide the preview. Then I want to load some forces at each of the vertices and then move them along z-axis downwards. So vertex cloud loads, we give the mesh, and I'll then bouncy solver. Check it out. As you can see, the points are moving instantly. So as usual, we need to reduce the speed. Firstly, we add the toggle and the button. I set it false, and also the button for resetting the bouncy solver, like this way. Check it out. And as you can see, as soon as I enable the bouncy solver, the points will be moved along z-axis instantly. I specify unit z for the strength, and then I minimize the strength. Watch this. False, true. As you can see, they are moving toward up. We can define the expression minus x, then we can flip the direction of the movement. Check it out. Up to this point, we have controlled the speed and the direction of movement of the points. In the continuation, we want the points to be collided with the object. This time, I want to use solid point collide to keep a set of points outside or inside a given mesh. Here we got the vertices by the construct mesh, and then we give the vertices to the points, and also we got the solid, which is the brep. Then by holding down shift, we can consider it as the goal objects. Let us set them in order and then show you the result. Check it out. The points are collided with the object and still they are moving downwards. All of them are falling. And the reason behind this, the points are not connected to each other and we don't have here the blanket, is because of the forces between the vertices. So by using edge lengths, as I told you before, we could have connected the vertices to each other and considering the forces between the points. This time, as you can see, the surface is fell on the B-wrap, which is exactly what we expected. However, we can increase the speed. Check this out. But here note that the vertices are getting too close to each other, as you can see. Here if I increase U and V counts, like 40, I reset it, check it out, and maybe increasing the value for unit Z factor. As I showed you, by increasing the number of the points or U and V counts, still we got a problem. Some of the points are crossing through each other and we haven't specified any constraints for them. So to solve this, we can minimize U and V counts to reduce the volume. Then in the continuation, we can use goal collision. In a sphere collide again, we add it into the canvas, then we give the points or vertices, then specifying a value for the radius, not 0.0 to 25 for the distances between the points, and then we reset the simulation again. Right now, as you can see, the distances between the vertices are considered, and it depends on the dimensions of the objects. However, we got another approach to solve this, is to convert mesh to a triangulation mesh. So we need to triangulate. We give the mesh the square meshes to have them in triangles or triangulation. And then let me move these backwards and then reset the process again. Check it out. Here we got a regulated blanket in triangles, and in order to display the blanket itself, we can use show, then giving the mesh and also giving it to the bouncy solver. Finally, we can use clean tree to delete the null items, then list item to extract the first item, which is the mesh. Then I bake it to check out the mesh, and then I can pause the converge process. Let's check it out. The blanket in the rendered viewport, but here as you can see, the object, it is still sharp. No, it is not subdivided. So to subdivide the mesh, we can use Weaver, Birds, Catmull, Clark as usual. 3 levels. Check it out. And after smoothing the object, still we can repeating the process. We can subdivide it twice. And as you can see, in compared to the previous one, it is smoother than the last one. However, we can use other tools like the tools in Mesh Plus. For instance, we can create a texture out of it. but I don't want to move on anymore since you can work on it. If you want it, you will be given the files. So just let us check it out. Firstly, let me move it and then position it at the origin point. Move it upwards, and then I want to associate a material in custom. Check it out. Let me specify the color. I select these kind of blue. Then in the rendered viewport, following that, I'm gonna start turntable command to orbit around the object by turntable, like this way, at the specified speed. And we managed to make such a thing, or in fact simulate it. In the continuation of physical modeling by using Kangaroo plugin, we're going to take a look on these pictures and check out the samples, and then we want to move the project forward based on an algorithm, and then we're gonna start modeling. And the website that I want to introduce is the nervous.com, or nervous system, that you can find brand new projects and also creative projects in, which are mostly related to the jewelries and customs. So I'm gonna tell you how to model these objects or these forms, and also you will become familiar with the algorithms of creating such a form. Or in general, we're gonna talk about differential growth and the associated algorithm that enables you to create attractive models. Here I'm gonna show you multiple plants, or the brain, and even the fingerprint, and other various things that we can imitate them from nature. I'm talking about the algorithms that you can find the natural version in the nature. So let me set these two windows apart of each other, and then we're gonna start. So firstly, I'm gonna draw a deformable circle in the rhino, and then I want to move the control points like this way. Check it out. After drawing such a form, then curve parameter, I set the curve into Grasshopper, and then we can internalize it and delete the curve in Rhino. Following that, we're gonna use divide curve to divide the curve into points like this way. Let me specify the number of points, 500, and then I want to convert these 500 points to some lines. Firstly, I'm gonna use polyline, as you are concerned that we can create polylines which are joined with each other, but I don't want to use polyline since I don't want to explode them later. So let us talk about line. We give the points, but what should I give for the next point? I want to connect the points to each other sequentially, so we can use shift list. Firstly, we give the list of points, and then it shifts the items inside the list. It moves the items. For instance, item 0 would be item 1, or index 1 in fact. So guys, check it out. We got the line made by using shift list, divide curve, and line out of 500 points. What about the next step? I wanna draw a surface. I draw a rectangle at first, and then curve. After setting the curve, I want to give it to the surface to convert it to a surface. Right now we're done with the surface that the curve is placed on. We can internalize the surface and delete the surface from Rhino. Following that, in the continuation in Kangaroo tab, I'm gonna use length as we used to work with it in the previous sessions. Then I specify the length between the points 2.5, I mean, each of the 500 lines will be 2.5 for the length. Then in the continuation, we search for unmesh to keep a point on a given mesh. And let me give the points, since I want to keep the points fixed on the mesh. But we haven't specified the mesh yet. Mesh BWrap. We give the BWrap to convert it to a mesh, then it would be supported by unmesh. So up to this point we have defined two conditions and also defined two targets. The length of the lines are at least 2.5, and also we wanted to keep the points on the specified mesh. If we do not use these, the points may move, so we use it to keep them fixed. Then bouncy solver by using boolean toggle, reset toggle, and then the button for resetting the bouncy solver. Check it out, and then we give the goal objects. Then we can hide the geometries, and then showing the preview of these. Following that, for V, we can add the interpolate curve to give V to interpolate and show you the results. Watch this. You can hide the preview and then set it true. Watch this. It was attractive. And I made a mistake. I give button to reset. Watch this. We can make such a thing. However, we can consider another condition that I don't want the curves to intersect each other by using collider. Firstly, we should give the objects, which are the 500 curves or lines. Then let me specify the radii 0.35 to the distance between the curves. Check it out, reset it. Here, as you can see, the specified distance is considered between the curves, but the bouncy solver is still running. Here, if I increase the strength of unmesh 150, check it out to minimize them, and also we can specify the length and strength, actually 100. Check it out, and 100 to the strength of collider, or even 200s. Watch this. No, I'm just specifying these values randomly. I just wanted to increase the strength. Then we can increase the number of points, 950. Well done. I delete the 2.5. Following that, we can specify one for damping. Let me connect it. The speed is lowered because of the running process and the high number of curves, 1000 for the strength. And let me minimize the radii and then resetting the process. Here, as you can see, this is the result. And let me minimize the length of the line, for example 0.5. Check this out. Then such a geometry will be displayed in the scene. And I increase the radii, or the distance between them, and then for the interpolate, I right click on P and then I invert it. And let me close this, and increasing the length 0.8, and let me minimize it, 0.55 or 0.4. Check it out, the reset, like this way, 0.2, and modifying the radii at point 15. Great. The 15 centimeters is considered between the curves. We can increase the length 1.8, for example. Check it out. And finally, we can draw such a geometry for ourselves. And the next example, we're gonna map this pattern or project it on the surface. So to do this, firstly, let us bake this pattern or curve in the Rhino and then internalize. Great. I set it false. Then by using a polygon, 8 for segments, for example, and following that, I want to extract each of the vertices by using discontinuity as usual. We give the curve, and then we will be given the segments and the points. Move. We move the points along z-axis, but about the shape of movement, I want them to be moved star-like. So first of all, I'm going to use range. Then let us define the domain between 0 to 1 at the number of these points. So list length, we give the length of the list of points, then we give it to number. Following that, we should give the range to f for the movement distance. However, I want to multiply it into a value in order to increase the amount of the value, like 25. Check it out, we got them by this way, star-like. Here we have used the range, however we could have used series instead of range, but the reason for using range was that before giving range to unit Z, I wanted to use graph mapper actually. So firstly we give the range, and since the specified domain is between 0 to 1, we can give it to graph mapper and modify the control points like this way. Check it out. I move them. Let me adjust the position. For instance, something like this. And finally, we can convert the curve to an interpolate curve. I make a copy from interpolate, and we give the points, and then the points of discontinuity to connect them to each other. Following that, we hide the previews, and we can have such a surface. Let's check it out by using loft. Watch this. Let me flatten the list and then check out the surface. So guys, we're done with the surface, and if I want to make the object better visually, we can scale it, give the geometry, then from the origin point, and then we give the geometry to interpolate, or even by shift list we give the list of points to move them. Check it out. This is the result after shifting the list. So let me move the control points to modify the surface. Then we can go for the other parts of the practice. Very well. And then 2 for the shift list. And as I told you before, I want to map the pattern on the surface. Let me run the process and reset it to check the pattern. and then the top view, in order to make it more practical, I want to minimize the length 0.4 and then reset the process like this way. Very well. And 0.05 for the radii of the collider. Check it out. And then after doing this, we can use the appropriate 0.8 for the length. Yes, as I was saying, we can use the appropriate tool to map it. Map to surface. As you're already familiar with it, we give the curves, as you can see, and also we should specify the base surface. Check it out. Let me connect the base surface to map to surface, and then we should specify the target surface, since we want to map it on the target. Watch this. We select all, and instead of the map to surface, and hide the geometry. Watch this. We got the pattern mapped on the target surface. After setting false and then multi-pipe, we give the curves to convert them to some circular pipes, and then the node size 0.15. Check it out. Let me minimize it. 0.2. And maybe I can minimize it. 0.04. This is better. And then baking the object. Finally, check it out in the rendered viewport in Rhino. Assigning white color like this way. So this was the first example related to the differential growth algorithms or patterns, and in the next videos we're gonna cover the others. We're gonna expand the examples and talk about it comprehensively. So guys, let us talk about other differential growth patterns. Here in Rhino, I have drawn such a curve, and I want to set it by using curve parameters. Set one curve, well done, then I internalize it so we can delete the curve in Rhino. Following that, let's divide the curve by points at 15. Great. Then at each of these points, I want to draw some circles. And I don't want the circles to intersect each other. Here, Kangaroo, bouncy solver, and even we can use solver, the simple solver instead of bouncy solver, because this is okay. We add the solver and then goal collision, sphere collide. Then I want to consider each of these points on the curve as some spheres. So first of all, let us convert these points to some polylines, just like shift list as we did it in the previous session. This time I want to use polyline as usual. Following that explode, we give the polylines the curve, then we will have multiple lines. Right now, each of these are independent to others, or they are separated or splitted. Then each of these segments are going to be converted to some springs, and then we give the points to create some spheres on them. In fact, spheres, yes. Then we give the spheres to goal objects, button, and the Boolean toggle as usual to turn it on and off. Then in the continuation, watch these circles, we add them. Then I should specify the radius of the circles, for example 1.25 for both radius and spheres and circles. I minimize it, 0 reset, and hiding the preview. if I increase the radius slowly, as I increase them, since the spring constant is high, the circles are crossing each other. So the first thing to do is to minimize the strength of length. So the default value is 10. I want to specify 1 for it. Check it out. This is the result. We have minimized the constant or stiffness. Check it out. The spring is getting shallow. Again, let me minimize the strength. Well done, and then resetting it. Following that for the radius, I'm gonna increase it slowly, like this way. Here, as you can see, as the circles are getting bigger, are pushing each other, and since I have minimized the strength, so the spring can be stretched. Let us move on here by using interpolate. Let's check it out. Interpolate, and then giving the vectors to convert it to some curves. We don't need the curves. Just check it out. Then we can delete the primary curve. We don't need these, we hide the previews. Then the count or the number of the points, we can increase them 100 or 1000 actually. 1000. And I reset this part and set 0 for radius. As I told you before, I wanted to increase them slowly, so I increase the digits or decimal places so I can maximize it slowly. And as I want to increase the specified radius too slowly, so I zoom in, and as I have increased the decimal places, I can click and drag it. Check it out with a low speed, and as you can see, we can draw such a form like fingerprint that you can find it in nature or other patterns. Right now, let me draw a different curve like this way, a 3D curve, not planar, and let me move the control points like this way. Then we're gonna have such an algorithm on this curve, so reset it, 0 for the radius, then let's change the curve. And we hide it, again, reset. This time I wanna increase the radius slowly. Check it out. It is fantastic. And finally, we can use pipe to convert them to some pipes at the specified radius. Great. Very well. Check it out. This is the final result that we have just made. Let me exemplify another case, another practice. We delete the created object, then by using mesh tools or mesh sphere, for instance, we add it into the canvas, can hide the previous ones, and this time I want to work on mesh sphere. We're gonna create these patterns on the sphere. So what should we do? Firstly, let us specify the radius of the sphere like 15. Check it out. And then considering the circle at the same amount of radius. Check it out. We got the circle around the sphere. Let me specify U and V count 16 and 16, or increasing it 35, 40. Very well. And then I want to divide the circle into some points. 120 for the number of the points. Check it out. And then we gotta belts, something like belts around the curve, and then polyline as usual. Then we explode it just as we did in the previous examples, and then convert them to some springs by length, specifying the strength 1, and then a sphere collide. Then here we need to do something else, that we need to keep these points fixed on the sphere. So on mesh, we specify the mesh and the points. So after creating the pattern on the sphere, we want them to be fixed. Then solver, we give the goal objects button and the Boolean toggle for reset and turning it on and off. Check it out. Let me align these components, and finally specifying a value for R, a radius for the spheres or sphere collide. Then interpolate, we want to connect the vertices to each other, and then invert it or close it. Check it out. So this is the final result, and I increase the digits or decimal places. Then as usual, we want to increase the radius slowly. Watch this. And in order to make the project simpler than before, we can reduce the radius 2, for example. Reset. And I increase the radius slowly again. Great. And of course, we can minimize the strength at 0.05. And finally, we can increase the count of points 600 and 0 for the radius and resetting the process. Then again, we want to increase it slowly, like this way. Check it out. This is the result that we have just modeled. Then we can increase the density, and finally we can use pipe to convert it to some solid objects. Boolean toggle for turning it on and off, and pipe for the end of the definition. 0.25 for the radius of the pipe. Then wait for a second. Check it out. But minimize it, 0.05. This would be better, I think. 0.11. And this is proper than before. We bake it to check it out in Rhino. Check this out, and finally we can have such a geometry for ourselves. I hope you enjoyed this session, guys. Don't forget to work on these two examples. In this part, as you can see, we're going to talk about the minimal surfaces, and we're gonna delve into some topics about them. When we are talking about the minimal surfaces, we expect a characteristics of a surface to be minimal, and at this topic, at this field, we're talking about the area. And when we are talking about minimal surfaces, the first thing that comes to our mind is the subfields that Fry Otto used it in his researches and explores. So he used them to create different kinds of geometries. And when you search subfield in Google, then you will be encountered with such geometries and such images, as you can see, that this vivid that they are created out of some bubbles. For instance, the rings are crossing through the bubbles, or for example other rings, and before the bubble getting collapsed or explode, you can observe such a model out of the bubbles. And one of the simplest minimal surfaces that we deal with it is catenoid, as you can see, as I have searched for it. Previously, we got familiar with the catenary topics or the chain-like objects that were connected to each other. And right now, if we rotate the catenary, we can create such a geometry. As you can see, we got two rings, and between these two rings, a bubble is made. And as usual, I used to give some theoretical information about the topics, then we will go into actions. So, as you can see, here we got the bubble between the two arcs. We got a minimal surface between two arcs or two curves, or a minimal area which is created by soap bubble or soap film. However, we got other model geometries for the minimal surfaces that I will show them later. So, the first minimal surface that I want to talk about it is a simple thing, and which is known as catenary. In fact, catenoid. So to do this, we're gonna disregard the Grasshopper and start the process in Rhino. As usual, I'm gonna add some drawings in Rhino and then continue the explanations. We close these windows, following that by using a circle from the origin point at a radius of 10. Here is the circle, and then I want to make a copy from the circle at 20 meters. Following that, I can connect these two circles to each other by a line. Following that, by using a line, I want to create the minimal surface, but before that we can rebuild it. However, we don't need to rebuild it right now, but I may use it in the two next geometries. Then it's time to revolve them. Check it out. We'll specify the curve to revolve and then the center or axis of revolve fully circular like this. Next time I wanna select a point, I have rebuilt it, and specifying degree 2 for the continuity. Then I start revolve command, then I revolve it fully circular by this way. And then in the last example, I want to increase the degree of continuity like this way. This time I enable record history. Then I can edit the curve or the surface even after creating the surface, and it will be updated. So we record the history, revolve the center, and then revolving it fully circular. So right now I'm gonna calculate the area of each of these minimal surfaces, and in order to obtain the area we can search for area command, and then we will be given the area. Check it out. This is the result. Here, if you look at these closely, we'll understand that the shortest curve between the two circles is the vertical line, and the other curves, as you can see, are longer than the first one since they are curved. And I make a copy from these curves or lines, and then I want to show you the length of each: 20, 20.37, and the last one 21.34. So as we had the shortest curve or line between the two circles in the first one, so let us obtain or calculate the area for each of them. I add the text, then in the text field I click on it. Here I click on area and then select object. I select the surface, then specifying the unit, it is per millimeters. Click on OK. Check it out. Again, OK. Then we can have the area of the surface. And I edit it. I just extrude the surface. to show you that the value or the area is being updated. Control Z to reset it, then again create text field, select object, OK. Let us check it out. Then for the last one, select object, OK, and the area. Watch this. Here, as you can see, as much as we curve the lines or we increase the degree of continuity, the area is being reduced. Firstly, it was 1256 and then 1137 and 1055. And as I told you before, we can select the control point and then move it, because we had recorded the history, and as we are moving the control point, we are minimizing the value of area. Check this out, 768. So after this point, we understood that as much as we increase the degree of continuity, it will gives us less value for area. In a way that here we got such a geometry, as you can see. I mean, there we expected more degrees for continuity. Then I select these and put them apart and I hide them. Then let us launch Grasshopper and start the process. Following that, we will get back to the explanations and consider them. Firstly, we search for the circle and then we add it into the canvas by this way. Then I specify the radius, which was 10, the same. Check it out. Following that, we're gonna use extrude. Then I give the circle, then I extrude the circle at 20 units. I should have specified unit Z and then the factor by this way. In the continuation, it's time to convert the surface to a mesh. We use mesh surface, we give the surface and then we convert the surface to a mesh. Let us specify U and V counts 20 in 20 for example. However, later we can modify it. Great. By this way. And as I told you before, if you wanted to show the mesh lines or U and V curves, display preview mesh edges. We click on preview mesh edges. Very well. After doing these, I want to convert these mesh edges to some springs. And following that, let me increase V count like 40. And then we're gonna convert the edges to some springs. To do this, here we can use mesh edges to extract the mesh edges, following that by using length line to convert them to some springs. But the shortcut method is using edge lengths, this is the shortcut. We give the meshes so it obtains the edges or extract them and then it converts them to some springs. So we prefer using this to shorten the process, and we can control length factor and also the strength. We specify the length factor with 3 decimal places, and the next task that we're gonna do is to keep the top and bottom parts fixed. So to do this, here we can use naked vertices. We give the mesh, check it out. These are the naked vertices. Then I want to consider the naked vertices as the anchors of the project. Check it out. Here we got the edge lengths and the anchors, and then by using bouncy solver we can make the model. We give the anchors at first, the naked edges or the naked vertices actually, to make them fixed or keep them fixed, and then I give the edges to call object and can show the meshes like this way. We select these, hide the preview, and then button for resetting bouncy solver like this way. Then in the continuation I want to minimize the length factor slowly like this way, and let me add the list item here as well. We give O output, return of bouncy solver. Here as you can see, one of the parts is fixed and the other part is being curved, and the reason behind this is the seam point or seam curve. Check it out, the line. In fact we got two rectangles or two surfaces within the surface. In other words, multiple vertices are overlapping. So here we can use mesh weld. Firstly, of course, we should give the mesh to mesh weld and then the output to naked and show. However, we can add other welds by using the installed plugins. So this is the result by using mesh weld or weld mesh to create such a model. Check it out. This is the result that both sides are curved at the same level of continuity. And the radius of the circles for the bottom and top are 10. The distance between them is 20, which is the exact model that we had in the previous examples. However, some of them were different in radius, and in order to obtain the area, we can search for area. We give the geometry, and then we give area to the panel, then we will be given the area. In order to display or observe this part better, I wanna use text tag 3D. For the location, we give the center of the model, and then for the tag we give the area to display the area value in a 3D tag, and then in justify we set it to middle center like this way as the value of area. So guys, we have made such a surface, and as you know, it was more close to the geometry that we called it cadenoid. And also we have calculated the value of area, 938 square meters or millimeters. That is greater than the third object, as you can see. And it couldn't be a precise value, since between these two circles at the specified distance or length, if we change the value of u and v counts, check it out, look, the given value for the area is changing, as you can see. So we cannot consider this as a minimum surface, since a minimal surface got a different definition, because a minimal surface is a surface which got the minimum area, or it requires the minimum amount of material to be constructed. So here we are making a mistake. Maybe we made a mistake in creating the minimal surface, because as much as we increase the u and v counts or the division, we are given different values for the area. So what is the exact definition for minimal surface? Let us watch the movie here. Here is a video about catnoids and the soap bubbles. You will be given the file and you can watch the complete file. And here, as you can see, here is the catnoid is created between the two rings or the two circles. And when we increase the distance between the two rings, the bubble collapses. Check it out. So there is a specific distance between them that should be considered. And when I was modeling them in Grasshopper or Rhino, I did not consider at this point that the distance or length between the two circles should be regarded or is significant. And as you remember, as I was increasing the level of continuity, the calculated value for the area was minimizing. So the first thing that you should put it into consideration is that there are some conditions that they should be regarded if you want to create a minimal surface. So let us repeat the process of modeling these. I want to extract the circles like this way, and then I paste them here, but this time I want to move the circle at 10 units downwards, and then I want to draw the curve. Check it out. We got two circles, 10 for radius, and the length between them is 10 too. Half of the previous one, since previously was 20, I rebuild them. 2 for the continuity, and then I make 2 copies from them like this. Then just like the previous one, I want to revolve them. I specify the circles as the path. This time I increase the continuity, revolve, and then the axis like this way. And then for the last one, I want to record the history. Then we can control it after the object was revolved. Following that, I wanna use create text again to calculate the area for each of the objects. Watch this, 628. And the next one, fx, watch this, like 599, nearly 600s. And the last one, we calculated, then we want to modify the control point for the cross-section curve. We selected that first, and then in wireframe display mode, as you can see, as I'm increasing the level of continuity, the value of area is decreasing. Check it out. But from a specific point on, the area is increasing instead of decreasing. While in the previous example, as much as we increased the continuity, the area value was decreasing. So the more continuity, the less value for area. But here we had the opposite order, because right now the area of the third one is even greater than the first one. Check it out, and as much as I increase the continuity, the area is increasing too. So the mistake that we made was with the dimensions of the geometries, maybe. I mean, they weren't appropriate. So guys, we get back to the process, and I wanna make a copy from the number slider, and then specifying 10 for the extrusion. Following that, I disconnect these to build mesh. Here firstly we got a circle. We have extruded the circle and then converted to a mesh. So in order to rebuild the mesh. We want to modify or revise the U and V counts. Right now, as you can see, we got some rectangles on the surface, but I want to have squares instead of rectangles. So to do this, I want to specify U and V counts by the radius and the factor of the extrusion or extrusion distance. For instance, 10, which is the height or extrusion distance, can be set for U counts. Check it out, U counts. And then, U count is associated with the vertical lines or vertical divisions. Then here we can use a multiplication for specifying V counts. I search for multiplication to multiply 10 in the specified value like 1.5, and then I give the result to U counts. Right now I have multiplied the specified value for U count into 1.5, so right now height is associated with the U counts. And then for specifying V counts, we should specify the value by the perimeter. And in order to calculate the radius of the circle, the easiest way to obtain it, I'm talking about this circle. Here I can add the integer or number parameter, then we give the curve, then we will be given the perimeter, as you can see. Following that, I'm gonna use the multiplication for the perimeter as well. Check it out, we multiplied in 1.5 and then giving the result to V counts. So here, as you can see, the U and V counts, or each of the segments, the mesh faces, are equal to each other. So we got squares. But here, in order to specify a precise value for these, we can delete this part, and then I can use the circle formula to define the formula, which is 2pr. We add the expression here. Check it out. We can replace r with x and then define in the expression 2pr like this way. Check it out. Okay. Then we specify the radius. By this way, we multiply 2 in P and then in R, and then in the multiplication to multiply 1.5 in the value of perimeter and then giving it to V. Well done. Up to this point, we have extruded the circle and specifying 10 for the radius and also the height. Then I have used them in specifying U and V counts. And then for the seam point, we can use mesh weld, and we can repeat the process. And finally, here, as you can see, the area of the surface is changing. Check it out. By this way, let me specify 10 for the factor and 10 for this one, and then I want to minimize the length factor by this way. Well done. The value is fixed, 600.79. Control Alt H, and the specified value for the area for this surface is close to the new object. Check it out. Here the minimum value is 600, but the new method is better than the other ones. I mean, we should consider the height of the cylinder and also U and V counts. Here if I increase the B for the multiplication, when as I increase it, as you can see, the area is changing, but the change is not too much. Right now I'm gonna specify two different values for these, and when we specify different values, I mean when we run the mesh faces from square, then the area will be increased. The difference in area is considerable, so I wanna keep it in a square like for the mesh faces. I minimize B1, and then we can have the reasonable value for the area, which is 600.79. Very well, we managed to create such a thing, and you'd better to know that if we increase the distance or length between the two circles here, then we can call this a stage mesh relaxation, since we do some tasks for relaxing the mesh, and maybe so we cannot consider this as a principled minimal surface, but it is close to the concept of minimal surface. So for the first practice, we learned this. We select these and then we ungroup them. Following that, we can use the toggle, boolean toggle, and then ungrouping them and hiding the geometry. And let me select these. I want to keep them in the file, and it will be shared with these files. These files will be shared with you. Then about the Kangaroo, here we got two commands. Subfilm for generating zero min curvature meshes. Firstly, I'm gonna talk about subfilm, then we will talk about live soap, and of course we're gonna talk about other commands along with these, which is tsmooth. As you can see, it smooths a mesh only in the local tangent places and used in conjunction with subfilm. I mean, it requires subfilm, and if you want to use tsmooth, subfilm is required, and they should be used simultaneously. So here we can select these and make a copy from these. I make a copy from them. Great. And then we give the welded mesh to subfilm and tsmooth like this way, and then we add the bouncy solver. Let me search for it. Great. From Kangaroo plugin, we give the goal objects. From tsmooth and subfilm, following that, we add the naked vertices and also the anchor to give the naked points to the anchor. Subfilm and then show to the goal objects. Watch this. Here, as you can see, we have modeled a mesh or a net. Then here we can use triangulate to triangulate all quad meshes. Then we give the meshes the quad meshes, then we will have triangle meshes like this, and then after triangulating the mesh, we give it to show by this way. Again, we can use list item to extract the mesh. Watch this, and then return of the preview of the other objects. All in all, we have models such as geometry. I make a copy from area and text attack 3D to show you the area 599.20. So by using this method, as I explained, we can have a more precise minimal surface created by these two new commands or components that if I show you the primary surface, which was a quad mesh. This time I want to have rectangular meshes. Check it out. And then let us calculate the area 599.54, which is higher than the previous one. While in the previous example, the result was 618, so the difference was too high. So guys, disregarding the meshes, using soap film and T-Smooth can give us a precise result which are specialized for the soap film by this way. And in the next example, I'm gonna talk about the live soap. So we ungroup these, then you can use them. I add the boolean toggle and turning them off and delving into the next practice. For the next one, I want to model such a geometry. As you can see, similar to this form, but before that, let us observe multiple minimal surfaces. And usually the minimal surfaces are being duplicated by mirror. Check it out. We can model only one part of this and then duplicate or mirror it. As you can see, we can model one of the modules and then we can complete the other geometries by rotating and using mirror and duplicating. Of course, except these methods, we can use mathematical methods too. Here, as you can see, we got multiple formulas here that some mathematical operations are being used in the definition. As you can see on this screen, that these formulas lets you to create several types of minimal surfaces. And the plugin of Millipede was not included in your syllabus, but we will cover it. I will exemplify some cases by using the commands in Millipede plugin, that there you will be got familiar with these definitions too. And we may model some of these geometries. So I will share these files with you, don't worry, and if I forget, just in case, please remind me. Then I will show you the the PowerPoint file. Then let us talk about the last topic, which was modeling such a geometry. To do this, firstly, I want to draw a rectangle and then drawing 3 circles inside the rectangle by this way. And we can have the circles in various sizes. Check it out. And specifying different positions for them. Then we search for curve parameter, set multiple curves. We click and drag, and then we internalize them. Then we can delete them in Rhino. Following that, we can use boundary surface, giving the curves to create a surface like this. Then I want to convert the surface into a mesh. As you know, we got multiple methods. For instance, we can use mesh, and then we will be given such a mesh. Check this out. But the created mesh here, as you can see, it is not regular. No, some edges are no, the edges are not equal with each other. We got quads, we got triangles, and we can't control the sizes or the mesh. So we're gonna use mesh wrap. Check it out. To create a regulated mesh like this. However, I know of course it is not regular, but we can use mesh in utility to set the mesh and meet our needs. For instance, settings custom, check it out, and then we can refine the mesh for ourselves by specifying the values. For instance, we can specify minimum and maximum edges. If we specify 0.5 for each, check this out. It is regulated. And after specifying the minimum and maximum values, we will have it more regular. Then I want to use mesh edges. Check it out. We give the mesh. Then in the continuation, we want to extract E1 output. But what was the E1 output? E1 edges are edges that they got contact with only one faces, while E2 got contact with two faces, and E3 or E3 edges got intersection with three faces or more than two faces. So we give E1 to show you the naked edges. Watch this. Like this. Let me show you them by this way. Then the first thing to do, as you can see, we got 319 curves. But I just want to have 4, so we're gonna use join curves to join these. Check it out. Firstly, we join them by this way, and after joining them, check it out. Here, as you can see, we got 4 curves, 4 polyline curves. Then I want to explode them after joining them. Here you may ask, why should we explode them? And you may expect the same result before joining them. Let us check out the result. Watch this. Here we got some branches created by explode. Let me show them by prompt viewer. Check it out for branches. And these are the items. Show various items in each of the branches. So this was the reason for exploding and after joining them. Then I want to extract one point or one item at each of the branches. So we can use endpoints. We give the curves, we give the actually segments, and then I wanna extract the endpoints. For instance, the start, check it out, 1 for each. And as we had 4 branches, so I extract 1 item from each, then we will have 4 items. Like this way. Then in the continuation, I want to find these points on the curve. I want to determine that the specified point or the extracted point are related to which of the curves or which one of the curves. To do this, we're going to use curve closest point. We search for it, then we add it into the canvas. Following that, we give the points. Watch this, and then the curve by this way. Then let us flatten the least by this way, and then by using this one distance, we want to sort them. Firstly, we give the distances to key, and then let us specify the parameter of. Here we can disregard flattening the distance. Anyway, here we sort the items by sort list, and also we can assign some items. In fact, I'm gonna sort them by using the curves. We give curves to A, then we add the list item by this way. Check it out. Following that, we use move like this way along z-axis. Here, if I want to review the process, firstly I have added some points on these curves, and then I have determined the extracted points and the curves that they are associated to, and then we search for the gene pool. Let me specify the gene list editor for 2 and -5. Then here we got 4 values that I want to move them along z-axis. Check it out. After moving them, here as you can see, we got the groups or the sorted list. Right click and graph. Then we can move each of the curves independently. We can hide the previous parts and move on. And finally, we're gonna work on the points again. I want to keep the points on these curves. We can use onCurve component, and then let me find the points, the end point or the start points to the points, and then we give the moved curves since we want to keep the points on these curves. Then after specifying the inputs, we're gonna use live soap. Watch this. So for M output we should give the mesh like this way. We specify it, and then we got the U and V counts, and we have specified the points and curves as well. We add the button, and then by using bouncy solver we want to move the process. Check it out. Reset goal objects. Look, let me search for show to show the mesh itself, and here we can use the mesh to show. We connect it to show. Boolean toggle. Let me giving mesh to show, and then giving the result to the goal objects. And we add the list item for extracting the mesh. Let us hide the preview. Watch this. Here is the mesh, the minimum edge and the maximum 0.8. Then I reset it. Check it out. Great. Then we modify the movement distance or the movement factor, 0.5 for the minimum, or 0.5 for both minimum and maximum. Check it out. You know, it's like an animation. Modifying the movement factor. like this way. And then I give the button to R, since when we reset it we want the another one, I mean soap live, to be reset to. Then here we can consider this as a container which contains bubbles, and then modifying the movement factor. And here there is a maximum value for the movement. If the specified value exceeds from the maximum value, the model will be ruined. Check it out, just like a bubble, like this way. And again, for fixing it, we can minimizing the movement factor. We move it downwards, check it out, to be aligned with the others. Then we should reset it. Then we can have the same result. Check it out. Reset. And then modifying movement factor. Look, you can create such models by using live soap, and however we can move them along other directions by using vector xyz, and then we can graph the vector and giving it to the target, and then specifying x and z. I mean, I can move them along x and z axis. Check it out by this way. All in all, you can make these soap film and live soap. You can try other geometries like ovals and specifying different values for u and v counts. And then here, if we modify gem pool, we will have a more regular object. I set it to false in grouping them and hiding the geometries or the preview. So guys, we're done with the 3 practices or examples, and in the next practice, which is in the next session, which is the last session, we will work on more practices. Let us start the next practice. Concerning the minimal surfaces in mesh, I want to create a box for myself here from mesh box, and then from the origin point I draw the box at this height. Well done. After having the box, we open the front view. Then by holding down Ctrl and Shift buttons, we select top and face buttons, and then we delete them. However, I should have set the units and tolerances per meters and 2 decimal places for the precision. Well done. Following that, I want to set the mesh into Grasshopper, as you can see. Following that, after setting the mesh, I'm gonna weld the vertices. We give the mesh to weld the overlapping or duplicated vertices, and then pressing down Ctrl Q to hide the preview of the mesh. Following that, as I have deleted the top and bottom parts, I want to smooth them and then convert the geometry to a minimal surface. To do this, the first thing that I want to do is to extract the surface edges for top and bottom and then convert them to a polyline. So by using mesh edges, we give the mesh, and I click on draw full names to turn it off. Following that, mesh edges. Here we got the naked edges. Then I want to join the naked edges, or E1. Then we will have two curves, which are the mesh edges of the top and bottom parts. Here in fact we got two polylines that we can use rod to bend and stretch the resistance rod. We will have a smoother rod. Firstly, we give the polyline, then in angle factor, we specify the angle of each of these polylines. And here, as you can see on the screen, the angle factor here is 0 degree. Here, but we got 90 degree. Here I'm gonna specify 0 for the angle factor for all. So this part will be converted to 0 degree. In fact, by doing this, we're going to convert the quad to a circle, or to a circular polyline. And then for the axial strength, we specify the value like 30, we increase it, and 100 for the bend strength. Very well, after doing this, we add the bouncy solver, then we give the goal objects. Watch this. This is the result out of the mesh edges. As I told you before, we have made the circles for the top and bottom mesh edges. Then by using live soap, as I worked with in the previous episode, firstly we give the mesh and then we give it to the goal objects. We can hide the previous parts and we don't need to the mesh right now, so we delete it. And then in button for resetting the bouncy solver, and also for resetting the live soap to have it done. I internalize the mesh and then I delete the mesh right now. Again we reset it to show the objects. Here, as you can see, this is the result. Here there is a problem that when we reset the object, the top and bottom mesh edges are meeting each other, or the height is decreasing. That I don't want this, that we can use anchor to fix the vertices for ourselves, or to constrain them. So as we work with naked vertices, then I'm gonna consider the top and bottom naked edges for the anchor. Let us check it out, and then we give them to the goal objects to bouncy solver. Great, as you can see, we have solved the previous problem. The bottom and top faces or edges are fixed, but rod is disregarded here. Previously we had a circular object, but here the mesh edges are quad, so we don't have the circle anymore. So we understood that anchor is not a good choice here. What should we do? Well, to solve the new problem, we're gonna use anchor XYZ. By using this type of anchor, we can give the naked points, and we can constrain the points at the specified coordinations XYZ. For instance, in this example, we're gonna specify the points and constrain them along Z-axis. So we right click on Z and then we invert it, or we can set the boolean to true. Then giving it to goal objects. Watch this. As you can see, this is the exact result that we expected. Then by using the tools in Mesh Plus or in Weaver Birds, we can subdivide it like Weaver Birds loop subdivision to meet our needs and get close to the final object. But I want to move forward, I want to work on it more. So instead of using anchor XYZ, anchor XYZ was okay, it failed us in meeting our needs, but I disconnected since I'm gonna introduce another thing, which is plastic anchor. So firstly, we give the naked points to the plastic anchor and then giving anchors to the goal object. By using this command or tool, we can consider freedom for the anchors. For instance, for limit, the preset value is 1, that we can minimize it, not 0.5. In fact, we are minimizing the limitness, and I'm gonna use another thing which is grab. Let us check it out. And we can reset the plastic anchor that we can use button. Watch this. We have made the geometry, and finally we can use list item to separate the mesh out of the bouncy solver and have the other parts hidden, and then we can pick and move the corners. Here in plastic anchor, as you can see, there is a specific characteristics, which is the plastic behavior of the object. In fact, the mesh is flexible. Check it out, we can move them. Then it will return to its default mode. But if I move it excessively, check it out, it is fixed, just like a plastic. Check it out. So by using plastic anchor, you can modify the object by clicking and dragging, just like two metal rings in soap bubbles. And then as we move the metal rings, we can control the shape of the bubble. And this is the final result. And finally, I want to subdivide the geometry by loop subdivision. Watch this, and having such a result. However, we could have used Mesh Plus as tools like Snap Plus 1. You can find it in Mesh Plus subdivision. And let me specify the distance for the snap 1.23 by this way. And also welding the duplicated vertices and joining the meshes, following that welding them, and finally using weighted Cadmore-Clark subdivision to subdividing the objects. Finally we bake it, and then we can observe the final result in the rendered viewport in Rhino. Great. We delete this part since it is not required, and also we can delete it from Rhino, and the created geometry can be displayed like this way. I select these by click and drag. And if I want to work on it more, I can make a copy from the definition by this way, then I paste it, and then we search for Boolean toggle for turning the previous example off, and then I want to make some other modifications on the final result. Firstly, we bake the mesh, and then let me reset it, and here we can use a Boolean toggle to turn it off and have it hidden, And then by holding down Ctrl and Shift buttons, we can select some of these polygons and the mesh and then delete them or subtract them. Following that, after deleting these, again I want to set the new mesh that I have deleted some parts from it to set it into Grasshopper. As you can see here, we got a new boundary which is recognized by Grasshopper, and right now we can turn it on. Check it out. Where's the result? After resetting the process, in this example it cannot be consistent. And in the continuation, if I want to modify the position of the opening on the front face, check it out. Then I want to show you the result. Yes, check it out. Right now the dimensions or the size of the opening is accepted. We got the minimal surface. Meanwhile, the opening is considered 2. And then in Weaver Birds, we add mesh thicken. We can thicken the mesh at the distance of 0.25. Following that, we can subdivide it like this way. And as the grab is enabled for us, we can click and drag the object and make the changes upon the mesh. And finally, by using a custom preview, we can assign the desired color to display it better. All in all, in this example, we managed to work on some new tools and have a review upon them, just like rod and plastic anchors and anchor XYZ. I hope you enjoyed this session. See you next season.